Só que uma vez eu tive uma aluna que levou cobertor na mão. Mas eu vou trazer amanhã para pegar amanhã. Você vai contar até 5 para dar o início? Não, já pode começar. Good afternoon. It's a pleasure to announce that our speaker today is Dr. Daniela Olave-Rojas. She completed her master's degree at the Universidade de La Serena and her PhD at the Universidade de Concepción, both in Chile. Her research focuses on compact groups and clusters of galaxies. And she is a professor of physics and astronomy at the Universidade de Talca in Chile. Thank you, Daniela.
Thank you so much for the invitation. Well, as Angela says, my interest is focused on the galaxy evolution due to the environment effects, and my research is mainly developed in compact groups and in the galaxy clusters. Today, I talk about the testing clustering algorithms to search substructures within clusters, mainly using S+ data. We know that there is a relation between galaxy morphology and galaxy properties with environments. Galaxies with late-type morphology tend to be located in low-density environment, and also this galaxy displays blue colors, high star formation rate, and in some cases also has morphology affected by the environment. And galaxies with early type are located in high-density environment and displays low star formation, red colors, big size, etc. And through the years, several astronomers show that the morphology, star formation rates, colors, mass, and other galaxy properties are strongly related by the environment. Since more or less 5.5 gigayears, galaxies quench their star formation earlier in cluster than in the field. And also, galaxy clusters are the ideal laboratory for the study of the environmental drivers of galaxy evolution, because offer us a broad range of densities and also offer us a big number of galaxies in different environments, from the dense cluster cores to the sparse cluster outskirts. And in this sense, galaxy clusters are the ideal laboratory for develop any kind of study about the effect of the environment in the evolution of galaxies. And several authors found that the fraction of star-forming galaxies in clusters is always lower than the fraction of star-forming galaxies in the field, even at large cluster-centric radius, in the place when we expect to find similar star formation quantities or star formation of the galaxies. Also, through the hierarchical paradigm, galaxy clusters grow and increase their mass through the continuous merger of less massive structures. And in this way, it's very crucial and is very interesting to study galaxy properties in the outer regions of galaxy clusters, because we can connect the evolution of galaxies with the formation of the large structure like galaxy cluster. And also, due to galaxy clusters grow through continuous merger of less massive structure like galaxies from groups, or maybe galaxy fall directly from the file, or galaxy merger between other clusters, or the merger between filaments, for example. And it's very interesting the study of the properties of galaxies in these regions. Also, in this context of the galaxy evolution in the outer regions of galaxy cluster, several authors through the last 40 decades ago studied the fraction of quiescent galaxies in the outer region of galaxy clusters, comparing the fraction of quiescent galaxies in cluster with the fraction of quiescent galaxies in galaxy groups and in the field. And several authors found that the fraction of quiescent galaxies is always higher in the outer region of galaxy cluster. However, the galaxies that fall directly from groups, for example, has or display a high fraction of quiescent galaxies. This is very interesting because give us an idea that the galaxy group is the mainly environment in which galaxies quench the star formation before fall into the galaxy cluster. And this result cannot be explained by the effect, process, or mechanisms that galaxies suffer when passed within their 200 of galaxy cluster. Several authors propose that galaxies quench the star formation in galaxy group before they're entering in the cluster environment. And namely like these processes as the pre-processing. The galaxies are pre-processed in the progenitor groups and then fall quench into galaxy clusters. Several authors found that by simulation and theoretical work that it is possible to catch galaxies in galaxy group, inter-galaxy clusters, because galaxies retain some properties about the progenitor groups. For example, galaxies retain the kinematics associated to the galaxy group, even in galaxy cluster. And we can catch and identify substructures within galaxy cluster that correspond to galaxy group that fall in the past into the cluster environment. And in the outer regions of galaxy clusters, it's more easier to identify galaxy groups and substructure because retain several properties related with the progenitor groups. For example, densities, X-ray emission, and anything. However, the first difficult to overcome in any study about the pre-processing and galaxy evolution in substructure is the determination of the substructures because it's related or is limited by the data and the quantity of data, the quality and the quantity of data. And several authors through the years developed different techniques to identify substructure into galaxy cluster. For example, some authors using X-ray emission to identify substructure as a peak in the X-ray emission. However, this technique is biased to the high mass environment. Other authors use, for example, the velocity of the galaxies to identify substructure within galaxy clusters. However, this technique is biased to galaxy that has a very different kinematic with respect to the galaxy cluster. And other authors using, for example, density of the galaxies to identify different substructure as a collection of a high number of galaxies in the projection of the clusters. And through the years, the majority of the technique developed to identify substructures is focused on the spectroscopic sample. However, the spectroscopic sample is limited and has put an error associated to the low statistic in our sample. And in the case of S+, offers us a good opportunity to increase the statistic using a photometric sample in order to identify substructure or other structure, for example, increase the statistic in clusters or increase the statistic of galaxies that we can observe in file, for example. And in this way, the identification of substructure in a survey like S+, that is mainly photometrics, is very hard because in principle, we have information about the position of the galaxies in the sky and an estimation of the photometric redshift that this always has an error associated to the estimation. And for this reason, in the last time, I focused my interest into identify substructure in cluster with the idea to have a technique or a tool or a criteria to identify substructure with different techniques in order to improve the identification of the substructure and also in order to have an first idea about the substructure in cluster and then to confirm this identification using, for example, photometric redshift, and including the error of the photometric redshift, or in the case of the spectroscopic redshift, considering the spectroscopic redshift in order to see if the substructure is real or not. And for this reason, I focus my analysis in prove the clustering algorithms in order to assign galaxy to different substructures. Well, I start my analysis using Dressler-Checkman test in order to detect. I put sub in parentheses because through the last 3 or 2 months ago, I'm using and apply this technique in superclusters in order to identify cluster within superclusters. Well, I start the analysis and the study about the identification of substructure using Dressler-Checkman test. Dressler-Checkman test is a very powerful statistical test that I need the position of the galaxies and the spectroscopic redshift in order to compare the velocity of the galaxy with the velocity of the main clusters, defining a number of minimum number for the substructure. And Dressler-Checkman test, the original Dressler-Checkman test, give us a parameter named delta that is a weight or a probability that indicate the probability of galaxy that belong in a substructure. And high value of the delta correspond to the high probability that galaxy belong in a substructure. However, this test doesn't assign galaxy to single substructure. Nowadays, there is this plus that is an improvement of the Dressler-Checkman test, in which you can put several values for the minimum number of a substructure, and also you can assign galaxy to different substructure, considering the spectroscopic redshift of the galaxies. However, as I mentioned at the beginning of the presentation, the problem with the Dressler-Checkman test is that you need the information about the spectroscopic redshift. And this idea started some years ago when I started my PhD, because the idea was to put galaxies in different substructures using a technique, and that was independent of my age, because in this moment, all people that assign galaxy to different substructures using Dressler-Checkman test put galaxies hand to hand in different substructures. And the idea was to search for different tools that we can use to put substructure or galaxy within substructure, considering a physical parameter of the galaxies. And then, through the analysis and through the investigation about this technique, I find the Gaussian mixture modules. That is a technique in which you assume that a property of galaxies is a collection of n Gaussian. For example, in this case, you can fit 3 Gaussian to the velocity distribution of the galaxies in this cluster, and you can identify 3 structures or substructures within the clusters. However, the problem with the Gaussian mixture models is that in some cases we have a poor sample of galaxies, and you see a 3 Gaussian or 2 Gaussian because in this part you have a lack of data. And also, when you have a big number of data, in some cases you only can see 1 Gaussian, and it's very difficult to separate the distribution of galaxies using, for example, redshift or velocity fitting n Gaussian. And also, another improvement about the Gaussian mixture models is using Gaussian mixture model in 3 dimensions, considering the position of the galaxies in the sky and also considering the redshift of the galaxies. And in this way, you can identify different structures in the sky. However, the problem of the Gaussian mixture models is that all points are assigned to a single groups, because this Gaussian mixture models or this technique doesn't an astrophysics technique. It's a technique that developed for another topic, or another that can be used, for example, grouping people, cars, or anything that has a probability to belong in a groups. Gaussian mixture models is based on the probability of one point as part of one groups. And for this reason, all points in the sample are assigned to each groups. And in the case of the pre-processing analysis, this is a problem because you need to identify galaxies that would be part of a groups that fall into the cluster, but aren't or is part of the clusters because all galaxies in the cluster aren't part of a substructure. Because in a sample, for example, of a single cluster, you have 80 or 100 galaxies, for example. And these 100 galaxies, using Gaussian mixture model, all are assigned to different groups. And for this reason, I'm in my search about the clustering algorithms in order to assign galaxies to different substructures. I found the DivScan, which is a clustering algorithm based on in the density of the points. And DivScan is a clustering algorithm in where you need to put as input the minimum number that you considering the minimum number in a groups, and also you can put a distance that correspond to the radius to search the identification of the substructure. And DivScan is an iterative clustering algorithms in which the algorithm stop in a galaxies and search about the neighboring galaxies, and assign galaxies in the substructure if galaxies has the minimum number within the radius that you define as a threshold. And galaxies that don't fall or out the substructure are assigning by a label -1 that correspond, in the case of the DivScan, a noise, because DivScan is density-based spatial clustering of application with noise. In the case of the galaxies that are part of the cluster, however, aren't part of the substructure, the DivScan put a label has -1. And the problem of the DivScan is that it's a density-based algorithm, and in the areas in we have low density, we haven't seen substructures. When in the cases of we have a poor sample, for example, in the case of the spectroscopic sample, in which sometimes we have areas without galaxies, or one galaxy, two galaxies. These galaxies are not assigned to different substructures. And in order to combine the clustering algorithms and improve the development of clustering algorithms, I developed Calzagos, which is a Python package that select cluster members and identify substructures in and around galaxy cluster using mainly clustering algorithms, GMM, and DivScan in the one version, in the first version. In the second version, I'm including the HDivScan, which is a clustering algorithms based on in a hierarchical clustering algorithms that is work better when you use, for example, superclusters. And Calzagos was testing using the mock catalog developed by Pablo, using the S+ mock. And in my first version of the Calzagos, my interest was to identify substructure in and around galaxy clusters. However, nowadays, I need to identify structure or substructures or clusters in superclusters or in big areas, for example, in the Fornax area. And also the first version of Calzagos is not very good to identification of the substructures using DBScan when you have a big area, for example, to identify a cluster or structures. And yeah, well, in this plot, we can see an identification about the cluster members and substructure using Calzagos. To identify cluster members in Calzagos, I put two functions. One function is only by the spectroscopic sample, in which you need the position of the galaxies, and also you need the spectroscopic redshift of the galaxies, and also you need to put the escape velocity of the clusters. And in the case of the photometric determination from the cluster members, you need the position of the galaxies, and also you need the redshift of the galaxy, photometric or spectroscopic redshift. And in order to select galaxy members for the clusters, I perform a fit of n-Gaussian to the distribution of position and redshift. And then the software performs a 3 sigma clipping in order to remove the file interlopers. And in this plot, I put the identification of the cluster members and the identification of substructure as if the sample is different. However, the cluster is the same. In this case, you have the identification of the spectroscopic members and the spectroscopic substructure using only the information about the spectroscopic sample. And galaxies with different colors correspond to galaxies in substructures. And galaxies with a gray point correspond to galaxies that are part of the cluster, however, aren't part of substructure. And in the case of the inner part of the cluster, we have a substructure because I'm using a criteria that I define in Calzagos for the photometric sample. Because Calzagos has a very strong perform in the outer regions of galaxy clusters. And in the outer regions of galaxy cluster, the precision of Calzagos is about 85%. And the completeness of the substructures are 100. However, when I identify a galaxy within 1 or 200, the precision fall more or less 70%. However, the completeness fall around 40%. And this is due to, in the inner regions of galaxy clusters, you have very big numbers of galaxy or substructure that are projected over other, and due to Calzagos use clustering algorithms based on in the probability through the Gaussian mixture models, and also based on in the density of the point. In the central part of the cluster, the density is very high. For this reason, we cannot separate galaxies considering different substructure projected over other. I can, however, the precision is and the completeness is low. And in the other plot, you can see the same cluster. However, in this part, I identify cluster members and also identify substructures considering only photometric information about the cluster. And the identification of the substructure in both cases is, or I run Calzagos in independent way. And as you can see, is very good because in the case of the photometric sample, we can recover some substructure that appears in the spectroscopic sample. And also in the case of a substructure, for example, here, We haven't in the spectroscopic sample because the sample of the galaxies in this part are non-galaxies. And also when we use photometric sample, in some cases, some substructures appears more concentrated, for example, in this part. This substructure has 1 or 2 galaxies that correspond to galaxies in this substructure. However, I don't say that is the same substructures. And also in the photometric sample, you can see several substructures because you have more data. And all techniques that use photometric or spectroscopic data to identify substructures depend on the quantity of data available. And for this reason, we can see several substructures in the photometric sample than in the spectroscopic sample. Also, clustering algorithms are very powerful because it doesn't introduce a bias in the kind of galaxies. Because through the clustering algorithms, you find galaxies in substructures that are located in all parts of the color magnitude diagram. You can identify blue, red, or green galaxies. And also, in order to test and develop a cross correlation between the substructure identified in the spectroscopic sample with the clustering algorithms with the substructure identified, for example, with other technique, I develop or I perform the Dirichlet-Checkman test in the spectroscopic sample. And in this case, galaxies with high values correspond to galaxies in the square, and this galaxy has a high probability to belong in a substructure. And if you can see, for example, these 3 substructures are identified using clustering algorithms and also appears when you use Dirichlet-Checkman test. And also with the Dirichlet-Checkman test, I include galaxies in the inner part of the clusters as galaxies in a substructure because my idea and my interest is not only develop a technique to identify substructure because I'm interested in correlate physical properties of the galaxies with the environment of the galaxies. However, this is the start of the problem. And in the case of this substructure, I doesn't include in the analysis because yes, has a high probability to belong of a substructure, however, are in a low density area. And for this reason, these galaxies is not included as part of the substructure. And also, in order to analyze the kind of galaxies that are part of the substructure in the spectroscopic sample, I'm perform the phase space diagram, and I'm very happy because I find that the majority of the galaxies in substructure are located in the first infrared region of the phase space diagram. And in this way, I can see and can say that the galaxies in the identified substructure using the clustering algorithms are galaxies that are for a first time in the cluster environment. And in this way, I can study the relation between galaxy groups that inform galaxy cluster and compare with the process or compare with the properties of galaxies in the clusters. And also, at a first step, with the idea to correlate one properties with the environment, I use color bimodally to separate galaxies in blue and in red colors. And in the case of the spectroscopic sample, I have galaxies in substructure within 1 or 200 because I'm including the galaxies that are catched with the Dirichlet-Checkman test. And as you can see, the fraction of galaxies or red galaxies in the outer region of galaxy clusters is higher in substructure than in the galaxy cluster. And also the fraction of blue galaxies in outer substructure is higher than in the cluster. And this could be due to that the environmental, in this case substructure, play a role in quench the star formation of galaxy traced by the colors. And in the case of the spectrophotometric sample, it doesn't include galaxies in the inner regions are part of the substructure because I'm using a technique and I'm restricting my identification only for the outer part of galaxy cluster. However, if you see the outer region of galaxy clusters, 3 or 200, you can see that the results are the similar that in the spectroscopic sample. And then, in order to characterize in a better way the environment of the galaxies, in order to correlate other parameters, for example, with the evolution of galaxy and the transformation of galaxies, I'm also work in the estimation of the density of the galaxy, however, using a proxy that is the distance from the 3 nearest neighbor distance, or the 5 neighbor distance, or anything you can put the number that you prefer. Why I use 3 neighboring galaxies? Because my first analysis in my scientific life was with compact groups. And my idea is that in the case of the galaxy cluster, you can identify substructures that are or could be maybe a compact group, for example, falling into the cluster environment. Interestingly, in this case, this big substructure corresponds to the other cluster that is merged between this cluster. And in this case, you can see that the distance or blue colors correspond to a little distance from each galaxy to its 3 neighboring galaxies. And in this case, this could be correspond or is related to the density of the galaxies. And galaxies in blue colors in this part correspond to galaxies in a high density regions. And you can see that these structures and the center of the clusters that correspond to the gray point is or appears in both plot. Also these structures and this. When you increase the numbers of the galaxies in substructure, disappear some substructures. This is due to the performance of the DB scan. And in the case of the 10 galaxies, sorry, yes, no, in the case of 10 galaxies, we only see one group that doesn't appear in this plot. And due to I test the HDB scan in order to identify galaxies using clustering algorithms. And when you use a HDB scan, that is an improved version of deep scan, you can see that you can identify different substructures when you use 3 samples. And in this case, the estimation with HDB scan is more or less better. However, when you can put more galaxies as a minimum number that a substructure could be contained, we have a better result using HDB scan. And in the case of 10 galaxies, you can recover different substructures that disappear when you use DB scan. This is a very good point, because in the case of the big sample and in the case of the big area, you need to recover this part of the cluster. In these cases, the central part of the cluster and the whole galaxy with gray point and correspond to galaxy to this main structure. And for this reason, the other clusters are identified as substructure of the principal or main cluster in my analysis. And well, this is Fornax, and in the case of Fornax, we have a problem because it's a very big catalog and area. And yesterday, I performed a test in order to see if the clustering algorithms could identify different structure in Fornax. However, in this case, I performed the test in a blind way, without physics and without astronomy or astrophysics parameters. This corresponds a fitting of n Gaussian to the all galaxies in the catalog of Fornax. I put a high number of Gaussian. I don't remember if I put 50 or 60 number of the Gaussian. And in this case, the Gaussian mixture modules fit 45 or 45 Gaussians. And how the Gaussian mixture model select the best number of Gaussian through an iterative process considering the Bayesian information criterion. And you put the maximum number of Gaussian, and the software select the best number of the Gaussian. Interestingly, Rodrigo yesterday passed me, or this week, passed me through two clusters that are real cluster in the Fornax area that correspond these two. And if you can see, these clusters are located in the area that Gaussian mixture models considering as group, only considering using the position of the galaxies. These areas correspond to Gaussians considering only the position of the galaxies, without information about the photometric or spectroscopic redshift. And then I ran DBScan plus GMM in order to identify different structure in the Fornax area. And when I put the HDBScan, I obtained the same result. In all cases, I'm using Haber-Syn metric. That is a metric very useful for you have a spherical surface in order to determine the distance from galaxies considering the spherical shape of the sky. However, when you use the Euclidean or Haber-Syn metric, in the case of one single cluster, you obtain the same result. The metric is important that you change to the Haber-Syn metric when you work with a high area or in the sky.
Which is supposed to find a Gaussian around the point, create such straight line boundaries between.
Yes. I doesn't study in this case why the shape, why is the shape of the areas. I think that is due to the probability of the galaxy to belong in a different Gaussian, and because it's very interestingly, because in this case, this is an artifact due to the observation in the Fornax area, and this is now is removed in the new catalog, and Gaussian mixture models identify this as an Gaussian in the area. However, the shape, I know that depends of the covariance, that in the case of the Gaussian mixture model, I put any kind of variance and any kind of shape, and also any kind of Gaussian available in the software. Yes, I know. Yes, it's very tricky. Well, and a summary is the HDBScan is better in the identification of substructure in big sample, and the metric distance is not crucial in cluster. However, it's very important when you have work with a big areas and big sample. And the identification of substructure or structure in the case of Fornax, considering only the position, works very well. The next step in the case of Fornax is to include the photometric redshift in order to can separate galaxies considering slices in the redshift space. And in the next step for Calzagos is include the photometric redshift, the photometric error, and also the probability to belong to a galaxy to different structure or substructure, depending on if you want to identify clusters or other structure, for example, in the case of the Fornax. However, in the case of the Fornax, I am very happy because the cluster that Rodrigo identified is one here, and the other is this in this part. And only using position of the galaxies, you can see several structure or areas in which would be a structure, for example. Thank you for your attention.
Thank you very much, Daniela. That was a very nice talk. I'd like to ask if anybody has questions. Laerte.
In this case, I don't know, because in this case was a very fast test in order to see if the clustering algorithms find something, only using position of the galaxies and without astrophysical parameters. I only put the input catalog that Rodrigo gave me, and I see to the Gaussian mixture models identify N Gaussian using this Hasabic number.
In the case of Fornax, we know that photometric redshifts are not very efficient. Anyway, you can try to verify whether the structures are real by their magnitude distribution. Because if they are at the Fornax distance, you should expect a similar magnitude distribution than the clusters, the members that we already know.
Well, Analia suggests me, in the case of the Fornax, include magnitude, for example, as a parameter in the case of the when replacement of the photometric redshift due to the problem to the estimation of the photometric redshift in the case of Fornax. Another, but not in the case, really in the case of the Fornax, but another technique to identify substructure could be identified using spectroscopic redshift and then to add more galaxies in the substructure identified by the spectroscopic information. But in this case, it was only a very fast test.
Yeah, I believe magnitude distribution, but maybe also size distribution. Yes, would be a good way, yes. Anybody else would like to make a question? Okay, good, wonderful.
Hi, Daniela. Thank you for your talk. I was wondering if you are considering the photometric errors in your estimation of substructures.
No, at this moment, not. However, the next step is to include the photometric error in the estimation of the substructure. At this moment, to identify substructure considering the photometric redshift, I'm using the photometric redshift like a spectroscopic redshift. However, the next step for Calzagos in the second version, the idea is to include the photometric redshift and the error of the photometric redshift in order to put as in the output the probability to belong a substructure considering the error in the photometric redshift. However, in this part, not yet. Thank you.
Hello, Daniela. Thank you for the talk. It's very interesting. My question is about the purity and completeness that you calculated. You said you recovered the substructures with 90, I think it's 100% completeness and 85% purity. Is it right?
Yes, I'm using to estimate the completeness and the precision of the software. I'm using F1 score and also using the mock catalog. In the case of the test clustering algorithms, I considering the information in the mock as the real. However, in the case of mock, I clean all halo that has 1 or 2 galaxies because I put an input that a subtractor is a belong of a 3 neighboring galaxy at least. And then using the typical equation to estimate completeness, purity, and F1 score, considering this information.
Okay, and the mock is the one from Pablo?
Yes.
Ah, okay, nice. Ah, very interesting.
Yes.
Any further questions? Okay. Just to make me run, I know.
Thanks. I was thinking about add not just the redshift information, but the peculiar velocity information. Would it be useful and can it be done?
In the case of the spectroscopic redshift, yes, I am using photometric information or the peculiar information, the peculiar velocity in 2 ways. In one way to select cluster members, and in other way, I also can use the peculiar velocity of the galaxies in subtractor with respect to the subtractor. For example, at this moment, with Claudia, we are working in a cylinder in a cluster, and the idea is to identify subtractor in front and in the background of the cluster. And in this way, you can use and you can measure the peculiar velocity for each galaxy with respect the halo, for example, or the groups. For example, it's only by the spectroscopic sample. In the case of the photometric sample, no.
Okay, very cool. Thanks.
Thank you very much. Any other further questions? If not, I have one very quick one. Daniela, I think that you have the idea of in the future making some constraints on the size and also the delta Z of each of the substructures. How do you plan to do that?
At this moment, I don't know. I'm reading the literature because I think that maybe due to there is a probability or some equation to measure the probability to belong in a cluster members. And the idea is to include, for example, this equation in the determination of the members of the subtractor. However, at this moment, I don't know why include this parameter.
I think this is a good idea. And then once you know who are the members, you can calculate the mass. And then given the mass, you can have a typical radius and a typical delta V. That could be maybe a way forward.
To edit photometric redshift, or photometric members to a spectroscopic subtractor, I'm using this technique. I estimate the velocity dispersion of the
spectroscopic
sample, and then I estimate the like an R200 radio or a radio for the structure, and then I put within photometric sample. However, in the case of the only photometric sample, I don't know at this moment how include this parameter. Maybe it could be estimate a parameter like the sigma, but considering the error, for example, in order to edit galaxy.
Yeah, I think
in
it's very
difficult. In the case
difficult.
of the spectroscopic sample, is more easier because you have a very precise estimation about the velocity of the galaxy. But in the case of the photometric estimation, it's more rude the determination of the subtractor.
I agree.
In the past, also, I tried to develop a technique like the Dressler-Checkman test using the photometric information and error of the photometric information, but the result is
very bad. Very bad. Yeah, that's why I think that what is viable would be to always use the spectroscopic sample as your guide, and then just use the photosys to complete the spectroscopic sample.
And
that
for this reason, this identification was performed in an independent way
Yeah.
because
I see. So
it-
this
this
shows that it
substructure
works. Yeah.
is this.
Yeah.
However, in these cases, I doesn't include a photometric member considering the spectroscopic information.
Yeah.
I perform the identification of the substructure in an independent way
Yes.
in order to see if I can catch the same substructure
Yes.
or
Great.
some substructure. One, I don't know. In this case, worked very well. The
Yeah,
identification.
I think it works very well, but when you want to put a size and a delta V, then I think it's nice to be guided by the spectroscopy.
Yes.
Spectroscopy, yeah. Thank you so much, Daniela. Let's just thank Daniela again.